Hello again. So we're getting to one of the best parts of the course now, where we get to play with some models and do some experimentation. And so far we've looked at how to evaluate our model. So we've looked in particular at 4 metrics for evaluating our model. So those are the mean absolute error, the mean squared error, the root mean squared error, and the sum of residuals. Before we go on to looking at how to improve our model, I just wanted to introduce another library which is very useful in data science, called scikit-learn. And as we've said earlier, there's a lot of possible metrics that are widely used in data science and machine learning. So it's probably not surprising that some of those have been collected up into useful libraries. And one of the most useful of those is scikit-learn. So we'll just take a quick look at that one. Just move that down a bit. Okay, so scikit-learn does machine learning in Python, which includes a lot of data science stuff. And you can see some examples there, but in particular, if we take a look at the API and we have a look up in our index here, we can see that there's a package in there called metrics, and if we have a look at that, we see that there's a bunch of different metrics that you can use in model fitting. And if we have a look down here, we'll find mean absolute error, mean squared error, and actually mean squared error here also does root mean squared error, depending how you set this last parameter here, squared equals true. So if you set squared equals false, you get the root mean squared error value. So that's a really handy package, and although there's no problem with our own mean squared error function that we've defined, there are sometimes advantages in using methods out of a library. Sometimes it gives us cleaner and more maintainable code. But there can be pluses and minuses, so I'd like to have a think about what might be the pluses and minuses of using a published method versus using your own defined method. So I've listed here some of the pluses and minuses that we might think about. So firstly, efficiency. Assuming that the library comes from a reputable sort of source and is a popularly used library, you can usually assume that they've come up with a pretty efficient implementation, and there's a lot to be said for not reinventing the wheel ourselves if we don't need to. Reusability of the code, so the code's obviously made to be reusable and to have parameters and things that make it generalizable or reusable in lots of situations. Again, we don't need to write those ourselves. Working in distributed teams, so it may be that you're working here, other people in your company are working, for example, in Europe or the US or in Asia, Africa, any number of other places, and the use of public libraries affords a degree of standardization. So it makes it that much easier to ensure that your code's going to be interchangeable. On the other hand, if you're thinking about the longevity or the breakability of code, how useful libraries are depends a little bit on how stable they are. So often there's a lot of development going on. So I might write some code this year, and then next year I try and run that same code, and I find out that it doesn't work. And the reason is that I haven't changed my code, but the library has changed. Someone's updated the library and it no longer works. So I have to try and debug it. So there are some pluses and minuses there, but in general it's good to make use of reputable third-party sources. So to demonstrate that, we'll use the scikit-learn version of mean squared error for the remainder of the case study, and I've given it here an alias because it's got quite a long name on its own. So now we're going to have a look at improving our model and ways of trying to find a really good model, optimizing the model. We've already seen an example of where we can improve the model by changing one of the parameters. So here we just reduced the intercept, which moved this line. Remember, the line here is our model, and balanced up these residuals a bit more. We also saw an example where it didn't work out so well, where we tried to change the slope and we made it a lot worse. Intuitively it was quite hard to change the slope because the y-intercept is so far away that a little change in slope makes a very big change by the time we get to the dates that we're interested in. So what we're going to look at now is how we might do this, and we're going to start by just shifting things so that we can make the changes in slope a little bit easier and a little bit more intuitive. And the way we're going to do that is just by shifting our coordinate system. Effectively, we're just going to move our xy axis, or move our y-axis in particular, so that it goes through the middle of the region we're talking about rather than 0. The 0 here is arbitrary, of course, because it's the date 0 years. So the way we're going to do that is just by subtracting the same amount from all of the dates. Okay, so we're going to work out where the middle is by just working out the median, and we can see that in this case it's in 2007, and then we're just going to map the dates to a new set of dates, which is just the old set of dates minus the median. Okay, so that means that 0 will end up in the middle of our range, and apart from that, everything else is the same. The slope doesn't change, nothing else changes. So here's a plot of our model again, with the coordinate system changed so that 0 is in the middle here. And our intercept, of course, changes because it was way up to the left there, and it was, I can't remember what the value was, something like 343. So now it's 2.125. Okay, so now we can try again altering the slope and see if we can get a better result. So let's do another small change to the slope. This time we're going to just add 0.05, which is rather smaller than what we added to the y-intercept, because a small change in slope makes quite a big difference. So here's the plot again, where we've increased the slope. So because it's a negative slope, I think you're seeing it that way around. If we increase the slope, we actually flatten it out. And so here's the plot with the slope increased by 0.05, and we've again worked out the mean squared error. So you can see that we've reduced the mean squared error now from 1.37 odd down to 1.14 odd, just by that slight change. And you can sort of see that by looking at it. You can see that the residuals here are a bit more balanced up once we've flattened it out a bit. Okay, so you can see the improvement in the mean squared error as that line flattens out. So what does that tell us already about the ABC plot? Okay, well, it tells us that the ABC plot is not it tells us that the trend line they've used in the ABC plot is not a good resemblance or a good model for the data that they've put up. Okay, I don't know whether somebody has just drawn that trend line in. It looks like that's the case rather than actually calculating it. Why is this so important? It's important because we now have quantitative evidence that justifies our qualitative hunch. Okay, so by looking at it, we thought, well, it doesn't look right. But we now have quantitative evidence that says that that's the case. It's not right. Okay, so we can now be concrete about that assertion. So let's see if we can do a bit better again. So we saw that we can improve the intercept a bit, we can improve the slope a bit, and we can get a better model. So let's try doing both of those things at once. And we find that our mean squared error now has dropped down to 0.9 or so. Okay, so we get a much better result by doing both of those two things. So we could keep doing that. We could keep adjusting things ourselves manually. We try and bump the slope a bit, see if it improves. We try bumping the intercept a bit, see if it improves. And we can kind of keep doing that to see if we can get a better and better model. But that's going to be a fairly slow and laborious process. And we've got Python on hand, and why not ask Python to do it? Okay, so we're going to do a search for better parameters and therefore a better model, and we're going to use Python to do that search for us. Okay, so how will we do that? The first thing we're going to do is make our rotations a bit more intuitive, because it's not very intuitive. You know, the slope is expressed in terms of the rise over run. If we increase that by 0.05, what does that really mean? Intuitively, we've got a good idea of what it means to change something by 1 degree, or 90 degrees, 45 degrees. So let's start with just defining a method, rotate, that rotates our slope by a factor phi. That's the Greek letter phi. Okay, and that just uses the tan. It's just using Pythagorean geometry and trigonometry to define the rotation. So for example, here we've got a rotation by 1 degree, and you can see that 1 degree is less than what we got from our 0.05, because our 0.05 gave us an error of 1.14, and our error is now increased to 1.26, so we haven't reduced those residuals as far. Okay, so what we want to do now, we said we know we can keep manually changing those and see if we can get better. What we want to do is we want to see if we can automate that process. We can do that using an iterative approach.